Okay, so this answers the standard. I can describe how a current loop experiences a torque in a constant magnetic field. 75 from chapter 27. Rectangular loop as a wire shown in the figure. I recreated it. It's kind of tough to see, but it served its purpose for me. And has a mass of 0.15 grams per centimeter of the length and is pivoted about its side AB on a frictionless axis. The current in the wires is 8.2 amps in the direction shown. Find the magnitude and direction of the magnetic field parallel to the y-axis that will cause the loop to swing up until its plane makes an angle of 30 degrees with the YZ plane. Okay, so I started off with the torque, like setting the torques of the non-magnetic field torques, so I could solve for what that value had to be. And I struggled with it for a long time until I realized that you can just simplify it and do like the center of gravity in the middle there, which in that case the radius is going to be half that of this length here, and then I had to do some math up here with the perimeters, like how much length it was, divided by the mass per centimeter that it gave us. So then I also had to do some trig to find out the value, but it was pretty easy. So then for the torque, I said that since torque is force times radius perpendicular, that the mass times gravity, that was the force, and then the radius perpendicular was, I think it was 4 centimeters? Yeah, 4 centimeters, which yielded this value. So that's what had the torque had to be in the equation with the magnetic field torque. I don't know why I had this equation, I didn't end up using it. So then I solved this for B to get B is equal to torque over current times area times sine phi, where sine phi is perpendicular to the, I think it's like this way, it's like the, I don't know why, norm is like the, it's perpendicular, so it's going to be the complement to 30. And then I plugged in my values, so I had this torque which I put in here, and then it gave us I, and then, well, I had to solve for the area, which was, I think it's, yeah, no, where is it? Whatever, I multiplied 0.06 by 0.080, 0.0048. And then, like I said, it's the complements of the sine of 60, which is square root 3 over 2. And then I solved that to be 0.024 teslas for the magnetic field. And that is in the direction parallel to the, no, that is parallel to the y-axis, yeah. Okay,